Good morning, students. We still continue with two-component system in this visual lecture. Let us not forget that during the previous lecture, we also spoke extensively about the one-component system. And for one-component system, we have said that the variance is equals to 3 minus p. Whereas when we talk about the two-component system, it means that the variance f, it will be equals to 4 minus p. One component system, good people, they are normally applied to compounds such as water, carbon dioxide, and others. I also believe that during the previous lecture, we have also shown some of the phase diagrams for both water as well as carbon dioxide. Okay, for two-component system, I want us to take an example of distillation, because in this particular example, we can be able to show both the dependence of vapor as well as liquid composition upon the mole fraction. I think in a nutshell, like the main difference between one component system and two component system is that for one component system, as the name suggests, we only have one component. But for two component system, like in this case, we do have two components. Namely, in this instance, we have the vapor and we also have the liquid composition. Okay, moving forward, the other question that we can ask ourselves is, what is distillation? What is distillation and why distillation is so important? So when we talk about distillation, we are basically referring to a technique that is normally used to separate a volatile liquid from a non-volatile solid or a solid. So typically in a distillation setup, like in the laboratory, as we can see from the diagram, we normally have a setup that consists of two flasks. So one flask, as you can see, it is heated. And in that particular flask, we are having a mixture that contains maybe two liquids. It can be liquid A as well as liquid B. So the other flask, as you can see from the diagram, it is normally used to collect the volatile distillate during the process of condensation as well as heating. So what I'm trying to say is that during this process of distillation, we have a mixture that contains both liquid A as well as liquid B. And both liquids, they mainly differ in terms of their boiling points, and they also differ in terms of their volatility. The one that is more volatile, it will be transferred from that mixture into another flask. There are a number of examples whereby distillation is very important. Like, for example, a distillation of herbs for perfumes, and also distillation of herbs maybe for medicine. So even the distillation of alcohol. So ladies and gentlemen, this is a typical phase diagram for two-component system. So in this particular system, we want to show both the dependence of liquid composition as well as vapor composition on the mole fraction. So as you can see in our graph, we want to plot the graph of pressure versus the mole fraction of A. Remember that within our mixture we have A as well as B. But in our case, it means that liquid A, it is more volatile than liquid B. As you can see from this graph, it simply shows that when we increase the pressure of our system, even the mole fraction of our system will also increase for both the liquid as well as the vapor. So in our graph, as you can see, the upper part is whereby we are having the liquid composition, and the bottom part is whereby we are having the vapor composition. So in our graph, Like point A. Point A, it represents the vapor pressure of a mixture of composition XA. And point B, it represents the composition of the vapor that is in equilibrium with the liquid at that temperature. And all the points that lie between the two lines, they correspond to a system in which there are two phases present. One phase being the liquid and the other phase being the vapor. So if you want to summarize the previous graph, this is how that particular graph it can be summarized. We have the graph that shows the relationship between pressure as well as composition. So for the upper part, I think from the previous graph, it was the liquid. It means we only have one phase in that instance. So when we have one phase, we know that F is equals to 2. For the bottom part of our graph, as we can see for the vapor composition, we also have one phase. And when we have one phase, it means that F is equals to 2. Remember that we have also shown the points between A and B. And for those points, I said that is where we have two phases. And when we have two phases, it means that F is equals to 1. Okay, to further discuss the distillation, we need a temperature composition diagram instead of a pressure composition diagram. Why do we need a temperature composition? Because during the process of distillation, we are basically heating our mixture while we are also condensing our mix. So such diagram, they normally shows the composition at different temperatures as well as a constant pressure. Normally the pressure is around 1 atm. So this is how a typical diagram that shows the dependence of mole fraction with temperature looks like. Remember that for the graph of pressure and mole fraction, when we are increasing the pressure of our system, it means that the mole fraction, it was increasing. But for temperature and as well as mole fraction graph, we can see that when we increase the temperature of our system, what happens with our mole fraction? We can see that the mole fraction of our system, it is also decreasing for both the vapor composition as well as the boiling temperature of the liquid. The temperature composition diagram corresponding to an ideal mixture with the components A being more volatile than component B is shown in that particular graph. So in that graph, it means that we are having the successive boiling and condensation of liquid originally of composition A1 that will lead to the condensate that is pure A. So as we can see from our graph, like if we start at A1, so when we increase the temperature of our system, it means that where we see A2 or at T2, that is where we are going to have the boiling temperature of our liquid. From A2 to A2 prime, it is whereby we are going to condense that particular mixture. And after condensing that particular mixture, if we further boil our system or our liquid, we are going to have a new boiling temperature of our liquid at T3, which is A3. If we further condense our mixture, we'll have A3 prime. And from there, if we further heat, the other new boiling temperature will be at A4. From this particular graph, what we can see is that through the process of successive boiling, it means that even the boiling temperature of our liquid will also decrease. So this is a typical setup for fractional distillation. We can have two different types of distillation. Like the first picture, I've shown a graph of simple distillation. So this one is a typical graph for fractional distillation. So in a fractional distillation, it means that we are having the boiling and condensation cycle that is repeated successively, as we have shown in the previous diagram. So this diagram simply shows or summarizes the relationship between the temperature, composition, when we have the temperature as well as the mole fraction. So for the pressure composition diagram, this is how the graph will look like. So this particular graph, ladies and gentlemen, I think you can look at this graph in your notes as well as textbook. Similarly, even the isoprolif composition in each phase of this diagram. Where is the diagram of pressure versus the mole fraction of ZA? I think you can also look in your textbook in terms of how to analyze this particular diagram. I think, ladies and gentlemen, for this particular lecture, which was very, very short, we are done. Thank you for listening.